Hi folks, welcome to the 3.1 video part 2. And so before we start any new problems, I want to go ahead and make a correction based off of what we talked about yesterday, okay? I think we were all getting a little tired, you folks less so than me, because most of you caught the mistake, but I wanted to take the time here to go ahead and make sure that we are aware of what went wrong. The good news is that 95% of it was correct. I won't say we, I goofed in one of the last few steps, okay? So when we approach these problems, and the ones with Newton's law of cooling or warming, we're still going to follow the same 3 steps, this idea of solve the differential equation, apply the initial conditions, and then make sure that we are answering what the question wants us to answer. So all of our setup was correct, our applying the initial conditions was correct, and we just need to come down here and I need to make sure that I don't goof my algebra, okay? And in fact, I'm going to keep what we have because I think it's important to see sort of what's right and what's wrong. And so I'm going to go ahead and in blue, I'm going to put the correct answer, okay? So we're good. Actually, I'll use purple. We're good up until here. And this part right here, let's write this in the red. This is incorrect. And we're going to make our corrections on the other side. All right. So what was fine is I took this 68 and I subtracted it to the other side, and then I divided both sides by 12. That part is correct. And so I can still write 30.6 over 12 equals e to the natural log of 10.5 over 12 t. One thing I want to do, and this is why I often write more parentheses than necessary, I want to go ahead and make sure I know that I am multiplying this natural log of 10.5 over 12 times t. And so my mistake here was thinking the natural log applied to all of this, when in fact it only applies to one of those terms. And as such, I'm going to have to log both sides. Okay, so I'm going to natural log both sides. That part will stay the same, except I won't get rid of the natural log here. There'll still be a natural log of 10.5 over 12 on the right-hand side. So we'll end up with natural log of 30.6 over 12 equals natural log of 10.5 over 12 times t. And now we can isolate our t, and let's see what we end up with. We'll get t equals this natural log divided by that natural log. And when we put this into a calculator at this step, we can go ahead and round to maybe 3 decimal places. Actually, I think 2 might be sufficient in this case. So we'll say t equals 7.01. And I think it goes 0.36, but because it's a 0 next, I'll truncate it here. So 7.01 hours. Okay. And so what that means for us is that when we get to our interpretation, it turns out that this body was went from living to non-living 7.01 hours before the body was found. And I just want to double check a computation here, make sure we're okay. All right, so we've got that natural log divided by the second natural log. And we should get a negative value. So I'm going to go ahead and scooch this over because that negative value, I think, makes it much more clear why we're counting backwards in time. Okay, and that was something someone had pointed out to me. Shouldn't we end up with a negative value? And whoever said that, you are absolutely correct, because what that means is that 7 hours before the body was found, that's when it was last at 98.6 degrees Fahrenheit. Okay, so let's go back to the question, make sure we've answered it. It says, how long before the detectives arrived at the crime scene did the victim die? And we can say that it'll be 7.01 hours before. Okay, and so that negative sign implies the before, but if we were to answer the question, we can just say 7.01. All right. So thank you for your patience. Thank you for your corrections on this. I'm glad that we were able to figure out the situation here, that it was just a small algebraic error, okay? But that's why I like to ask questions of you all on test day that are more conceptual, some computations, but more conceptual as well. So small things like that don't derail your entire answer, okay? All right, so we have one last section in 3.1, and that is talking about mixture problems, okay? And so with the mixture problems, we have this differential equation, dA dt equals R in minus R out, okay? And so I want to define a few things here. When we have our R in, what we mean by that is the rate that solution is entering a tank. Okay, so in all of these mixture problems, we're going to have a tank, we're going to have some sort of solution coming into it, and we're also going to have solution leaving the tank. All right, so R in stands for rate that the solution is entering a tank, and R out is the rate that solution is leaving a tank. Now, the rate in and the rate out are both going to impact the concentration of the solution, meaning how much salt is in that solution. And so dA dt is going to be the change in salt amount with respect to time. Okay, so dA dt, our differential part of the differential equation, talks about the change in salt amount with respect to time. Now we've got some initial conditions here that we're going to have A be the amount of salt, and at t equals or t sub 0, that's going to be our quote unquote starting time. And that might be at t equals 0, or maybe we choose another starting point depending on the information. And our A naught, that is our starting amount of salt. Okay. And so with these three variables and differentials, that's really what we're going to focus on in the next three problems. Okay, so we have far less variables than we do in the Newton's law of cooling. So hopefully it'll be a little bit easier to set up and keep track of things. But one thing we will have to do is make sure that we find the rate in and the rate out very carefully. Okay. And in fact, before we move on, let's go ahead and say our rate in is going to be in green. And if you have colors, let's say the rate out is going to be in blue. Okay, so rate in will be in green, rate out will be in blue, and the difference between them, right? The difference between them will give us the change in the amount of salt with respect to time. All right, so let's take a look at example 4. Example 4 says a tank initially holds 10 gallons or 100 gallons of brine solution containing 20 pounds of salt. And so a definition I want us to be aware of here Some of you, if you are into cooking, you may know that you can brine things to help maybe make the meat a little bit more tender. But brine means a salt water solution. Okay, so if you've never heard that word before, you can add that to your vocabulary. Brine means a salt water solution. And in this particular tank, we have 20 pounds of salt to begin with. Okay. At T=0, fresh water is poured into the tank at a rate of 5 gallons per minute, while the well-stirred mixture leaves the tank at the same rate. Find the amount of salt in the tank at any time t. All right, so we know based off of the wording in this question, when we see something about salt solutions and mixtures coming in and out, we are thinking dA dt equals R in minus R out. Now you'll notice we didn't do any sort of derivation because in these problems, what we're going to have to do is find our rate out and find our rate in so that we can create an equation here. And the equation that we come up with, some of them might be separable, might be a separable differential equation. It might be one that requires an integrating factor, okay? And so that should be something we should be ready to use any of the techniques from week 1 to solve these questions. So we're gonna start with the rate in and figure out what that is, all right? So rate in, I'm gonna use an equal sign, is gonna be the salt concentration in the inflow, meaning how much salt is coming in, like in pounds per gallon. And we're going to multiply that by the input rate of the brine solution, okay? Whatever liquid is coming in, we need to take care of the rate there. And if we look back in the word problem, we'll notice that it tells us that at T=0, fresh water is poured in. And fresh water means that there is no salt in it. So our salt concentration is actually going to be 0 pounds per gallon. I'm actually going to write this as an up and down fraction. So we have 0 pounds per gallon, just because I think it'll make the units make a little bit more sense, okay? Now I know 0 times anything is 0, but because it won't always be 0, let's structure out the rest of the problem. That way, when numbers change, we'll be able to modify this sort of format for other kinds of problems, right? And so what is the input rate of the brine? Well, it is coming in at 5 gallons per minute. And again, that's fresh water coming in at 5 gallons per minute. And so even though I know 0 times 5 is 0, the units of this answer are going to be pounds per minute, okay? So pounds per minute is actually the rate of the salt coming in. We're going to set up a similar one for the rate out, right? And we're going to take this same setup. I'm going to cheat because I have a technology that allows me to do that. All right. But instead of saying salt concentration in the inflow, I'm going to say salt concentration on the outflow. And instead of the input rate of brine, I'm going to say the output rate of brine. Okay. So the format is very similar, except in for in and out for out. And so let's see what's happening as the salt comes out of the tank. Well, whatever amount is in the tank, A of T represents the amount of salt. In fact, it represents the pounds of salt in the tank. And how many gallons are in the tank? Well, we have 100 gallons. All right. So this is another reason I really like to write the units, because they help me figure out what goes where. Okay. Now, what is the output rate? Well, it says that the well-stirred mixture leaves at the same rate. So that means we're going to say 5 gallons per minute. Now, we're not going to get a number here, and that's okay. But we are going to get an expression that will be useful because, remember, we have a differential equation that we want to solve. So we get A of t over 20. So 5 over 100 gives us 1 over 20, and we've got pounds per minute. Okay. So we've got a setup for our rate in minus rate out. Now we're going to put it back into this differential equation. So we'll get dA dt equals 0 pounds per minute minus the salt concentration, salt amount over 20. So that's pounds per minute. And our job here is to find capital A, the amount. How much salt is going to be left in the tank at any given time? Now, if we look at this and we say, I have a 0, I don't really need to write that, we'll notice that we get to negative A over 20 is what dA dt equals. Now, by looking at this, I hope we recognize this as a separable differential equation. So I'm going to do a little bit of algebra. I'm going to divide both sides by A. I'm going to multiply both sides by dt. So we have negative dt over 20. All right. So conventionally, we keep the variables, the one that we're looking for our solution on one side. If there are any constants or signs, we generally keep them on the other side. Okay. So I'm going to go ahead and integrate both sides right now. Integral of 1 over a dA equals negative integral of 1 over 20 dt. On the left-hand side, I get natural log of the absolute value of A. We're going to drop those absolute values because A talks about how much salt is in the tank. And since A will by default be a positive value, we can go ahead and drop those absolute values. On the other side, I get negative 1 over 20 t plus a constant. All right. We're going to exponentiate both sides. We get A equals C e to the negative t over 20. And this, my friends, is the function that will give us the amount of salt in the tank at any time t. Okay. So I thought we would start off pretty straightforward, all right? Pretty straightforward in two senses. One of our values on the input end is 0, right? So we only have to worry about what's coming out of the tank. The second thing that sort of comes from that same idea is we end up with a separable differential equation, and those are typically the easiest to solve. But if you're worried about, oh, I would like to do some more challenging problems, Judy, why don't you give us some more challenging problems? Well, we're going to take a look at example 5 and example 6, and hopefully that will challenge us a little bit more to think about other types of differential equation solving techniques we have. Okay. So here is example 5. A tank initially holds 100 gallons of brine solution. This time, it only contains 1 pound of salt. At t equals 0, another brine solution containing 1 pound of salt per gallon is poured into the tank at a rate of 3 gallons per minute, while the well-stirred mixture leaves the tank at the same rate. find the amount of salt in the tank at any time t. Then find the time at which the mixture in the tank contains 2 pounds of salt. So we'll have two answers that we need. One, we need a function, and two, we need to find an actual value. Okay. So I look at this, I see a brine solution, input, output. I know I'm going to have a differential equation of this form. And keeping in the color coding, we're going to call R out in blue and R in green. And the first thing we're going to find is our rate in. Okay. So let's go back up a little bit here. We said that rate in was going to be the salt concentration in the inflow times the input rate of the brine. And so I'm going to go ahead and grab this so that we can have that down here. All right. We've only done one problem, so it's probably best to refresh our memory on where these numbers come from. But our salt concentration on the inflow, well, there is 1 gallon, 1 pound per gallon is what they told us is coming into the tank. What is the input rate? Like how quickly is this coming into the tank? Well, 3 gallons per minute. We'll notice that the gallons cancel and we'll end up with 3 pounds per minute. So there's 3 pounds of salt coming in every single minute. All right, let's find our rate out. We're going to change our inflow to outflow, our input to output, like we did before. And we're going to fill in the numbers. So the salt concentration in the outflow, well, we're going to have a certain number of pounds. And how many gallons are in the tank? 100 gallons. So we've got pounds per gallon. And then it turns out that the mixture is leaving at the same rate. So that's going to be 3 gallons per minute. We multiply this out, we end up with 3A of T over 100 pounds per minute. This represents our rate out of the salt. And so now we're going to be able to go ahead and set up our differential equation. So dA dt equals rate in, which is 3, minus rate out, 3A over 100. Now we look at this, I see a minus, and my first thought is, ooh, I don't think this is separable. But if we manipulate this a little bit, by adding the 3A over 100 to both sides, we end up with something like this. And this, I hope we recognize as something where we need an integrating factor. Okay, this is a linear differential equation. So we're going to go ahead and find our mu. I should use a t here. Mu of t equals e to the integral of p of t dt. Well, our p of t is 3 over 100, so we end up with 3e to the 3t over 100 as our multiplying factor. Now, we have to go ahead and multiply our differential equation by that. And so we'll end up with e to the 0.03t. So I didn't want to write a fraction, so I turned 3 over 100 into a decimal. dA dt plus 0.03 e to the 0.03t times a. Is that a derivative of a product? Sure looks like it. That's good. That's what I want. Equals 3e to the 0.03t. All right, we're going to pack up that left-hand side. We're going to say you are the derivative of e to the 0.03t times a, which equals my right-hand side. I'm going to integrate both sides. That will get rid of my d dx. I'm going to integrate the right-hand side. I'll need some u sub for that. And I don't want to forget my plus c. Okay. So I did not show the integration here, but make sure that you are aware of where that first term on the right-hand side came from. And this is a good place where folks typically do an explicit solution, okay? So I'm going to divide both sides by that e to the 0.03t, and I'm going to get a equals 100 plus c e to the negative 0.03t. All right. Now this is almost our answer. What do we need to find in order to find a function that tells us the amount of salt at any time t? We're going to need to find the c value. So at this point, we're going to go ahead using initial conditions. And in our initial conditions, let's go back and see what those are. Well, it tells us that the tank initially contains 1 pound of salt. That means our initial conditions are at time 0, we have 1 pound of salt. So our initial condition is 0, 1. I plug those in, I get 1 equals 100 plus c e to the 0. And we're going to end up with c equals negative 99. That gives us a final function, a of t, the amount of salt, as 100 minus 99 e to the negative 0.03 t. Let's get that all on one screen for you. This answers the first part. Find the amount of salt at any time t. Okay. Now the next part, though, says find the time at which the mixture in the tank contains 2 pounds of salt. So they're telling us that a of t is 2, and they want us to solve for little t. So I did not space this very well, but thank goodness for cut and paste. I'm going to finish this problem down here, and we'll just move example 6 to the next page, okay? So the second part of example 5 is 2 equals 100 minus 99 e to the negative 0.03 t, and we are solving for t. All right. I'm going to add 99 e to the negative 0.03 t to both sides. I'm going to subtract 2. That gives me 98. I get e to the negative 0.03 t equals 98 over 99. Going to natural log both sides. And then I divide by the negative 0.03. Now, as a human, you might be curious, what is this number, right? This is a good point to turn it into a number, and to also keep in mind that everything is talking about minutes. So when it says how long, like what time it is, we should also make sure that we label that as in minutes. Turns out if you type this into your calculator, you'll get 0.338 minutes. And that is the time when there are 2 pounds of salt in the tank. All right, let's take a look at one last question. Oops, that's not what I want. This is what I want. Whoops, okay. So here's our last example, okay? So example 6. We have a tank initially holding 300 gallons of brine solution containing 20 pounds of salt. At t equals 0, another brine solution containing 2 pounds of salt per gallon is poured into the tank at a rate of 3 gallons per minute. When the well-stirred mixture leaves the tank, it is pumped out at a rate of 2 gallons per minute. Find the amount of salt in the tank at any time t. All right, we see a lot of brine and salt and water coming in and coming out. So that means dA dt equals rate in minus rate out. And our job is to find the rate in and the rate out so that we can figure out what our solution is, okay? All right, so we have rate in is gonna be, let's see, how much salt is coming in? Well, if we go back to our problem, it says 2 pounds of salt per gallon. So I'm going to write 2 pounds per gallon. And the rate that it's coming in, 3 gallons per minute. And when we multiply those, the gallons cancel. And we're left with an in rate. Salt is coming in at not 2 times 3, which is 6 pounds per minute. Okay, now we have to figure out our rate out. Okay. And our rate out is actually going to be a little bit different this time. It's going to be different for one specific reason. The well-stirred mixture leaving the tank, it does not leave at the same rate. In fact, it leaves a little bit more slowly than it's coming in. And so conceptually, we might say, as time goes on, we get more and more brine in the tank because 3 come in, but only 2 leave. Okay, so 3 come in, only 2 gallons leave. So let me tell you what the equation is for the rate out, and then let's figure out where some of these variables come from. So like before, when we say that we have A of t pounds, and before we used to say that it was just how big the tank was, 300 gallons. But this time I'm going to tell you it's 300 plus t, little t, gallons. And for my rate out, I have 2 gallons per minute. And so if I multiply these, I get 2A of t over 300 plus t pounds per minute. Now, I hope you are asking yourself, where did she get that t from? Why is it 300 plus t? And I will tell you, okay? So where does that t come from? It turns out that my rate in, okay, if I think about just how much is coming in minus how much is going out, so not including concentration, not like how much salt is coming in, but literally how much solution is coming in. We have 3 minus 2, or 1 gallon per minute. That means that every minute we get another gallon in the tank. All right, so after 1 minute, there's now 301 gallons in the tank. After 2 minutes, there's 302 gallons. After 10 minutes, there'll be 310 gallons. And guess what we're doing? Every time we have a minute go by, we are taking that value and adding it to 300. 2 plus 300 is 302. 10 plus 300 is 310. And so that's why in our equation we have not just 300, but 300 plus T, because that'll tell us how many gallons there are in the tank. All right, so when the input and the output rate are not the same, we do have to compensate for how many gallons we have in the tank. Now we're ready to say, hey, here's our differential equation. I'm going to say that is the rate in, like the capital R, the amount of salt coming in, 6 pounds per minute, the amount leaving, 2A over 300 plus T. Right? Now, knowing how the situation changes the equation, that's really important. Okay. I would, as you're studying for Tuesday's exam, make sure you know how to modify something for a given scenario. Okay. All right. So we've got dA dt equals 6 minus 2A over 300 plus T. I'm going to do a little bit of algebraic manipulation. dA dt plus 2 over 300 plus T times A equals 6. Wow, looks like we might have another linear differential equation on our hands. What does that mean? It means I better find that mu of t, which I know is e to the integral of 2 over 300 plus t dt. Now, how do I integrate this? Well, I'm going to need a little bit of u sub. I'll get e to the 2 times natural log of 300 plus t. We remember a handy trick that we can bring that coefficient up as an exponent. And unlike the mistake I made yesterday, now I can cancel the e and the natural log, and I end up with 300 plus t, the quantity squared. That is my integrating factor. Now, if you're asking yourself, why did Judy lose the absolute values here? Well, think about what we're doing. We are taking something and we are squaring it. That is always, always, always going to be positive. So since it's always positive, I can write parentheses instead of absolute value. All right, let's multiply in our multiplying factor, our integrating factor. 300 plus t squared dA dt plus 2 times 300 plus t squared over 300 plus t. A equals 6 times 300 plus t squared. All right, I can pack up the left-hand side. So I'm going to do that, and I'm going to integrate in the same step. 300 plus t squared times a equals 6 times the integral of 300 plus t squared dt. We can use a little u sub here to integrate. The left-hand side stays the same. The right-hand side, let's see, 6 over 3, that'll give us 2 times 300 plus t cubed plus c. Don't forget that c, right? That's part of what we're solving for. So if we forget to write it, we might also forget to solve for it. All right, now we got to find our initial conditions. So let's go back up, read our problem again. And initially, what do we have? 20 pounds of salt. Well, how do we write that as an initial condition? At time 0, we have 20 pounds of salt. So 0, 20. I'm going to go back down to my differential or to my solution. I'm going to plug in 0 for T, 20 for A, and we're going to solve for C. I'm going to get, I should probably divide here first. I'm going to get 2 times 300 plus T plus C over 300 plus T squared. Now I'm going to plug in 20. I'm going to plug in 0. And when all is said and done, you should get a massive number for C. Okay. Last step, all they wanted was a function. So we're going to go ahead and we're going to replace the letter C with this number C. And so let me shrink some of this a little bit so I can fit my answer down here. All right, so that's going to give us the solution of A of T equals 2 times 300 plus T minus 52, 200, 0, 0, 0, all over 300 plus T squared. And that fancy formula, my friends, will tell you how much salt is in this tank at any given time. All right. So with that, we're going to go ahead and stop this video. If you have any questions, you can reach out to me on Canvas or on Discord, and I would be more than happy to clarify. All right. Thanks for watching, folks. See you later.